Good morning, dear students. Today in this lecture we will discuss the properties of Fourier cosine transform and Fourier sine transform. So let's start the properties of Fourier cosine and Fourier sine transform. So we can say let f of x and g of x be two functions defined in the interval 0 to infinity. Then say first property, that is linear property. Linear property says that Fourier sine transform of a f of x plus b g of x equal to a Fourier sine transform of f of x plus b Fourier b say Fourier sine transform of g of x. So this is hold for plus and this is hold for negative also. So means fx plus bg of x equal to a f of Fourier sine transform of fx plus minus Fourier cosine transform of gx. And say one more property, that is modulation property. Say modulation property. Modulation properties. So we can say if Fourier cosine transform of f of x, that is fc alpha, and Fourier sine transform of f of x, that is fs alpha, then can say first property Fourier cosine transform of f of x cos ax, that is equal to half Fourier Fourier cosine transform of f alpha plus a plus f c alpha minus a. Second one, if f of x cos ax, say half f of s alpha plus a plus fs alpha minus a. And third property, third modulation property, that is fc f of x sine ax equal to half fs alpha plus a minus f, that is a sine, so it going to, this is cos, so this going to sine f alpha plus a minus fs alpha minus a. And fourth one is Fourier sine transform of f of x sine ax equal to half fc, say if take here minus fc alpha plus a minus fc alpha minus a. We want to prove first, say fc f of x cos ax, that is equal to, by definition, under root 2 upon pi 0 to infinity f of x cos, we can write as under root 2 upon pi 0 to infinity f of x, and we can write as cos ax cos alpha x a cos alpha plus a plus cos alpha minus a dx. Means we can say cos alpha into cos a plus minus sin alpha plus sin a. From here cos alpha cos a, here this is x also, and cos alpha x into cos ax plus sin alpha x into sin ax. So sin term is cancel out. So this is, we can say, here 1 upon 2 also will come, half 1 upon 2. So we can say half under root 2 upon pi 0 to infinity f of x cos alpha plus a x dx plus under root 2 upon pi 0 to infinity f of x cos alpha minus a x into dx. So we can say, as we know that, means here we can say Fourier cosine transform of f of x, that is equal to under root 2 upon pi 0 to infinity f of x cos alpha x dx. If you can say Fourier cosine transform of means you can say here f means say this is f alpha, here given that Fourier cosine transform of fx is equal to f alpha, simply we can write as fc alpha plus a, that is equal to under root 2 upon pi 0 to infinity f of x cos, simply alpha replaced by alpha plus a dx. So we can write here half fc alpha plus a plus, similarly for this can be written as fc alpha minus a plus fc alpha minus a. So we can say this is proved. Similarly we want to prove the second one, means second one says that Fourier, means second one is Fourier sine transform of f of x cos ax, that is equal to, by definition, 2 upon pi 0 to infinity f of x cos ax, and as this is Fourier sine, so sin alpha x dx, sin alpha x dx, this is can be written as 2 upon pi into 1 upon pi, so multiplied by 2 and divide by 2, so half, and this come means 2, say 2 sin alpha x cos ax can be written as sin alpha plus a x plus sin alpha minus a x. So simply write as 0 to infinity f of x sine, say we can say sine alpha plus a x plus sine alpha minus a x dx. So this can be written as under root 2 upon pi 0 to infinity f of x sine alpha plus ax plus sine means plus under root 2 upon pi 0 to infinity f of x sine alpha minus a x. Here say here means say dx. So simply say that this is the Fourier sine transform of alpha plus a, and this is Fourier sine transform of alpha minus a. This is proved. Now we prove the other. Similarly we can prove other. And now discuss one more property, that is change of scale property. Change of scale property, that is Fourier cosine transform of f ax, we can say 1 upon a f c alpha upon a. Here a greater than 0, and second is for Fourier cosine transform, that is f ax equal to 1 upon a Fourier sine transform of a means alpha upon a greater than 0. So we want to prove this. Simply we can write as Fourier cosine transform of f ax equal to under root 2 upon pi 0 to infinity f ax means cos alpha x dx. Here let ax equal to p implies that dx equal to 1 upon a dp, and at x equal to 0 p going to 0, at x going to infinity p going to infinity. So simply you can write as f ax equal to under root 2 upon pi 0 to infinity, say this is f of p and this is cos alpha, means here x is equal to alpha, x is equal to p upon a, means p upon a simply, and dx is equal to dp upon a. So we can write as 1 upon a under root 2 upon pi 0 to infinity fp and cos p upon a alpha dp. P upon a alpha dp means you can say this is the Fourier cosine transform. This is Fourier cosine f alpha upon a. Simply say this is proved. In same manner we can prove for Fourier sine transform also. Discuss one more property, that is differentiation of sine and Fourier cosine transform. So first property is Fourier sine means Fourier cosine, that is x. F of x can be written as d upon d alpha Fourier cosine transform of f of x, say d upon d alpha fc alpha. Sorry, this is fs, this is fs. Similarly, second one for Fourier sine x, f of x, we can say minus d upon d alpha, say here fc f of x. We can say minus d upon d alpha fc alpha. fc alpha, where fc alpha is Fourier cosine transform of fx and fs alpha is a Fourier sine transform of fx. Now we want to prove first one. So as we know that means say Fourier sine transform of f of x equal to under root 2 upon pi 0 to infinity e to the say fx sine alpha x dx. This is the Fourier sine transform. By definition, say this is fs alpha. fs alpha. Now differentiate with respect to alpha. Simply we can write as, say we can say this is 2 upon pi 0 to infinity, differentiate with respect to alpha. So fx sine alpha x means cos alpha x into alpha, sorry, here differentiating with respect to alpha, so here come x dx, and this is d upon d alpha fs alpha. So here this can be written as under root 2 upon pi 0 to infinity x f of x, x f of x cos alpha x dx equal to this one. Means finally we say that this is the Fourier cosine transform of x f of x. Fourier cosine transform of x fx, that is equal to d upon d alpha fs alpha. Say this is proved. In the same manner we can prove for fs f of x minus d upon dx. Means we start from this, means fx is equal to fc fx means fx cos alpha x, and if we differentiate with respect to alpha, then simply in same manner we get left hand side. So find the Fourier cosine transform of a to the power minus a square. Means first try to find the Fourier cosine transform of a to the power minus a square x square, and with the help of this we try to find the Fourier sine transform of this one, and Fourier cosine transform of this, and Fourier sine transform of this. So first find the Fourier cosine transform. Means Fourier, say this is here, say means f of x equal to e to the power minus a square x square. So Fourier cosine transform of this simply fc e to the power minus a square x square we can write as, by definition, under root 2 upon pi 0 to infinity e to the here under root 2 upon pi, e to the power minus e to the power means under root 2 upon pi 0 to infinity e to the power minus a square x square cos alpha x dx. You can see here e to the power minus a square x square is even function and cos alpha x is a even function. So this can be write as under root 2 upon pi into 1 upon 2, 0 to means say minus infinity to plus infinity, e to the power minus x square a square x square cos alpha x due to even function. So this can be write as, so this also can be write as say 1 upon under root 2 pi here means 1 upon under root 2 pi. We can say this can be write as real part. This is the representation of this, means simply say that real part means e to the power minus a square x square e to the power I alpha x means this is cos alpha x plus I sin alpha x, means simply say this is the representation of this one. So we can say that Fourier sine transform of f of x that is equal to 1 upon under root 2 pi real part of here under root 2 pi real part of this one minus infinity to plus infinity. Simply we want to convert this term as a square term and this is a real part of dx. Simply this we can write as, means simply here a square x square plus I alpha x we can write here minus a square take as a common x square minus I alpha x upon a square, and this can be also written as x minus I alpha upon 2a square, means I alpha x minus I alpha upon 2a square and plus I square alpha square upon 4a square. If we expand, see if we expand simply get x square plus I square alpha square upon 4a square minus 2x I alpha upon 2a square. So 2 to cancel out means, and this is so sorry, this is here minus, so this is minus I square alpha square upon 4a square. So this term is cancel out, so simply get x square minus x I alpha upon a square. So we can say in place of this simply we can write here means e to the power minus a square say x minus I alpha x minus I alpha upon 2a square whole square and 4. So we can say 4a to the power 4 dx, means simply we can write here minus infinity to plus infinity a to the power here minus a x is come out as a to the power minus minus plus, and this is I square, so minus again minus will come, so minus alpha square and alpha a square, so this is 4a square dx. 4a square is 1 upon under root 2 pi means real part, and this term will come out, so e to the power minus a square upon 4a square and minus infinity to plus infinity, and this is minus a x minus I alpha upon 2a square whole square dx. Simply we write here, means if we take, means let a x minus I alpha upon 2a square equal to p, means let a in bracket x minus I alpha upon 2a square equal to p. So simply get a dx equal to dp. And you see here at x equal to minus infinity, p going to infinity, minus infinity, and x going to infinity, p going to infinity. So here minus infinity to plus infinity, and this is come out a to the power minus p square, and this is dx means dp upon a. So we can write here 1 upon under root 2 pi, and here given is real part. So here means there is no complex term, so simply we no need to write real part, means 1 upon 2 pi and a to the power minus alpha square upon 4a square, and this a also, so we can say 1 upon a, and this we can write as 2 0 to infinity a to the power minus p square dp. Say means here p square and this is p square and dp upon da, and here alpha square and upon 4a square, means here there is no imaginary part. So 2 upon under root 2 pi a to the power minus alpha square upon 4a square, and this can be written as under root pi upon 2. So 2 cancel out, pi to pi cancel out. So simply we say that Fourier means Fourier cosine transform of this simply 1 upon a under root 2 pi a to the power minus alpha square upon 4a square. Simply finally means finally we get the answer. Say that Fourier cosine transform of a to the power minus a square x square equal to 1 upon a under root 2 pi a to the power minus alpha square upon 4 square. Simply we get. Now we want to find the Fourier sine transform of this. So we can say we want to find the second one, means Fourier sine transform of x a to the power minus a square x square, and we say that this can be, say this is f c alpha, say this is f c alpha. So means we want to find, means as we know that this is minus d upon d alpha and Fourier cosine transform of f alpha fx, means we say that minus d upon d alpha, here fc alpha equal to 1 upon a under root 2 pi a to the power minus alpha square upon 4a square. So simply if differentiate we get the answer, say 1 upon a under root 2 pi, and if we differentiate this simply get a to the power minus alpha square upon 4a square into minus 2 alpha upon 4a square. we say that fs x e to the power minus a square x square equal to, see minus is cancel out, we can write 1 upon a 2 under root 2 and a, this is a cube, say this is a cube, and alpha e to the power minus alpha square upon 4a square, means simply here minus and minus plus, so 1 upon means here a square, so a cube, 2 under root 2 a means this is a and a square, so a cube, 2 under root 2 alpha, this is alpha e to the power minus a square minus alpha square upon 4a square. Now we want to prove third one, means we want to find the solution of third one, means cosine transform of a to the power minus x square upon 4. As we know that here fc e to the power minus a square x square, that is equal to 1 upon a under root 2 a to the power minus alpha square upon 4a square. And for finding this, here simply write a equal to half, so we can say Fourier cosine transform e to the power minus x square upon 4 means a replaced by half, so under root 2 upon 2 a to the power minus alpha square upon 4 into 1 upon 4, so we can say 2 upon under root 2 a to the power minus alpha square, a to the power minus alpha square. Finally we say that Fourier cosine transform of e to the power minus x square upon 4 equal to, say this is means under root 2 a to the power minus alpha square, a to the power minus alpha square. So finally we get the answer. The solution of last one simply write as, means find the Fourier sine transform of x e to the power minus x square upon 4, simply write as this is minus d upon d alpha, and Fourier sine means Fourier cosine transform of this, Fourier cosine transform of e to the power minus x square upon 4. As we know that by definition Fourier sine transform of x, f of x equal to minus d upon d alpha Fourier cosine transform of fx. Here fx is equal to a to the power minus x square upon 4. So as we know that Fourier cosine transform of this one, simply write as minus d upon d alpha, and Fourier cosine transform of this means under root 2 a to the power minus alpha square. So simply we can write minus under root 2 means a to the power minus alpha square into minus 2 alpha, means finally we say that 2 under root 2 alpha a to the power minus alpha square. So finally we get the answer.